I'm going to take this point on sine, and as I drag it, I hope you see that at the top here, that your tangent's going to be flat.
Yes.
If your tangent is flat, its derivative is 0. Do you see in this part, like a roller coaster, everything's downhill? We'd all have negative slopes in that section until it gets to this flat part where it's 0 again. And the crazy, like, this is kind of beautiful. That if you just measured all the slopes and put them together, it works perfectly to the cos graph. The pattern is so beautiful. Like, what are the chances of that? It's crazy. And if we look at the cosine graph, okay, there's the sine graph, here's the cosine graph. It starts off flat, so it starts at 0. Then it goes negative slopes right away until it gets flat again. Now it's positive slopes. So in our notes, I'm going to tell you that it's not hard. Here we go. No, wrong one. Okay. In our notes, I'm going to tell you, you could get these easily mixed up because the derivative of sine is positive cos, but the derivative of cos is negative sine. So they're so similar, and one of them has to be negative. And if you just try to memorize something, your chances of mixing these up at times could be bad, right? Because they're so similar. And you're like, oh, which one has the negative again? And then you could run into problems. So what I like to do is go back to those applets. Because if you think about the graph, let's start with the cos one, because the cos one is negative. Look at the cos graph. I'll bring it back to 0, right? I can clear it out. As soon as you go to the right, do you see that you're going to be going negative? Makes sense that then you would have a negative sine graph as soon as you go to the right. If you look at the sine one, and I'll clear that one again. Drag it back to the beginning. Do you see that if you drew a tangent at 0, 0, it's already positive slope? I find for me,
attention all witches and wizards,
that
the
helps me.
Snack Shop is open once again in the Life Skills Room J4. If you are in grade 9 this time and wearing a costume, and if your teacher allows you to leave the class, please head down to the skills room for a trick or a treat. You'll have 5 minutes to collect your treat before you must return to class. Grade 9s in costume, come on down.
So I can see right away from the graph that it's going up, that its slope is positive. So for me, this helps me remember that the derivative of sine is positive cos. And the derivative of cos, going down right away, is going to be negative sine. As soon as I go to the right, my slopes are negative. I can draw a tangent right away. There we go, negative slope. Derivative of cos is negative sine. And so these are our 2 new shortcuts for today. And now we can do all sorts of questions with them. But to start us off, if we actually wanted to use the definition of the derivative, some of the shortcuts we've had, you don't have the skills. Like the math skills are like complicated to prove e to the x is e to the x. Like the one that doesn't change, it's a little bit complicated to figure that one out. Okay? That's not too bad, but a little bit. This one is doable. You use 2 of your limits you already know, right? We used the squeeze theorem to prove well, we didn't prove them, but I told you you could look in your textbook if you wanted to. You could use the squeeze theorem to show that the limit of sine x over x is 1 and the limit of 1 minus cos x over x is 0. So if we were plugging this into our definition of the derivative, we would have a sine x plus h minus a sine x over h. Do you see something you can do that you learned in grade 12 pre-calculus? If you wanted to simplify this or complify it, I don't know if that's a word, but it does get a little bit more complicated if we do what we can do. You have an alpha plus beta formula. Your alpha could be x, your beta could be h, and if you used your alpha plus beta formula, you would get sine x cos h plus cos x sine h minus sine x all over h. And on first glance, this doesn't look like it's very helpful. But if we have these limits in mind, we might be able to make things look like those limits. Deliveries. Oh, thank you. Volleyball. So I broke it up. And one of the things that I broke up, like you're wondering, well, why did you keep certain things together? I broke this one up because I like this sine h over h. Because the limit as h goes to 0, do you see that that would be 1? So I like that part. And then when I looked at the other part, I noticed that there was a sine x in common. And if I factor that sine x in common out, I get this, which I like. That matches up with one of our limits. If we break up our limits into those two, and then all of the different things multiplying, because you can do that with limits. This limit is 0. This limit is 1. There's no h's in the other ones. So we get sine x times 0 plus cos x times 1, which of course is just cos x. So technically, if you're a math purist, and you have been taught mostly pure math your entire lives, but sometimes when things get complicated, your teachers go, just believe me, it's true. Okay? Like think back to your teacher last year. Did they prove the alpha plus beta formula? Yeah. They just said, here, use this. Technically, that's not allowed. If you're a pure mathematician, technically, you're not allowed to use something unless it's been proven before that you can use it. There's a whole branch of mathematics that starts off with what are the basic things that we know from math? And everything past that has to be from those basic things. What are like the fundamental rules of math from which everything, including calculus, can be described? Can we break it down to those fundamental 5 or 8 things? And that's getting really nitpicky. Sometimes some of the proofs are like, they're too complicated. You'd like to move on. And that's okay. So we're like feeling all proud of ourselves here because we proved this, using a proof that we never were allowed to do because you never proved it. So that's a little bit shady math. But we can do the same thing with our cos x one. Write our definition. Use your alpha plus beta formula. And then when I look at what I have here, I see this first. There I have a sine h over h. And so I would break things up by taking that one on its own and putting the other one on its own. And just like the sine one, it allows you to factor things out. Do all of our limits. And this one ends up perfectly as negative sine x. Will you ever be asked to prove these? Not until university class. So these two questions are for like giving you an idea what proving something from the definition of the derivative looks like. Take a calculus class in university, your professor might expect you to be able to do this. But for AP calculus, it's never a long answer question that they'll ask you. And it won't come up on a multiple choice. So that would be quite the multiple choice proof. And then A is a huge proof, and B is a huge proof, and you just have to circle the one that's right. It's like, it must be Halloween out there or something. I think we're at 8 shortcuts so far. The rules, we have the power rule, product rule, quotient rule, and then specialties are e to the x, a to the x, like 5 to the x, ln x, now sine x, and cos x. 8 shortcuts. How many are there, you're probably wondering? I'm going to guess we're going to get up to like 18, another 10 shortcuts to go. So what shortcuts are here? Okay, this one's going to end up using 3 of your shortcuts. First of all, it's a product. How do you recognize a product? Is when you have two things multiplied together and there's x's on both the yellow side and the green side. If the yellow side was just the number 7, it wouldn't be a product rule. It's only a product rule when there's things that you can derivativize, take the derivative of, in both sections. So how do we do a product rule? Well, we keep our first one the same. Maybe. Oh, fail. Keep our first one the same. Derivative of the second one. The derivative of cos is negative sine. That's a new shortcut for today. Plus, keep the first one the same. And then the derivative of 3x to the 7. Well, that is your power rule. Bring it in front, subtract 1 from the exponent. By the end of this year, you will feel like you knew the power rule since you were 5 years old. It's like just common knowledge. You're going to use it so much, you're going to be like, when did I not know this? Well, like 3 months ago, you did not know it. You don't need to simplify. Okay? This is one of the, like, there's like these shortcuts, and this is why a lot of people say, well, calculus, that's too hard. Because they look at it, and if you don't know the shortcuts, that looks like magic. Like, how the heck did they, that is, what just happened? Right? But if you know the shortcuts, then it's not very hard at all. If sine x, f of x is sine x cos x, it's a show that. So first of all, you would do things like you normally would. I notice I have this times by this. I have a product rule because I have something with x times by something else with x. So how do I do the product rule? I keep my first one the same. Derivative of the second one. Well, the derivative of the second one, that's a new shortcut. Derivative of cos is negative sine. Then I keep the second one the same. And then I use another new shortcut. The derivative of sine is cos, which gets me negative sine squared plus cos squared. Maybe you recognize that as one of your double angle formulas, right? Cos squared minus sine squared. You could immediately, oh, I forgot the x, E3 error, there we go. You could immediately change that to cos 2x. So we have to know double angle identities AP really likes. Alpha plus beta don't come up very often. We needed the alpha plus beta for the proof, but I said they're not going to ask you to prove it. They will put lots of double angle identities, especially sine and cos. Tangent doesn't come up very. If you're like choosing one not to memorize and hoping for the best, don't remember tan. Because you can always change tan to sine over cos. Okay. You are allowed to use this as a shortcut, but we are going to figure it out. This is our new shortcut. That tan, it's on the next page.
Attention all minions and monsters. Once again, the Best Buddies Halloween Snack Shop is open in the Life Skills Room J4. If you are in grade 10 this time and wearing a costume, and if your teacher allows you to leave the class, please head down to the Life Skills Room J4 for a trick or a treat. You will have 5 minutes to collect your treat before you must return to class.
If you change tan to sine over cos, then you would have which rule, which shortcut? A quotient rule. You would have to keep which one the same? Keep the bottom the same. Hey, there we go. Take out my highlighter. I keep the bottom the same times the derivative of the top, which is a new shortcut. The derivative of sine is cos. Minus, keep the top the same. The derivative of the bottom, new shortcut. Derivative of cos is negative sine over the bottom squared. And we're supposed to get that this is equal to secant squared. Can you see it already? What's the top going to be? 1. Yeah, 1. But before that, it's going to be cos squared x plus sine squared x, right? And that's an identity that you know is 1. So we get 1 over cos squared x, and cos squared x is secant squared x. And this will be a new shortcut. Right? So every single function that we know, there's a shortcut for. So far we've done e to the x, ln x, sine x, cos x, tan x. Which ones haven't we done? Well, we're going to have to do secant x, cosecant x, cotangent x. There's going to be shortcuts for those ones. There's going to be shortcuts for sine inverse x, cos inverse x, tan inverse x, cosecant inverse x, secant inverse x, cotangent inverse x. Those are all shortcuts we still have to do. Those are identities. You don't need to write those down. Can you work backwards? Undo your shortcuts. If you have a negative sign, what was that originally? That originally was a cos. Yeah, x squared. And here you can use, what was it, 17? Is that the favorite number?
Yeah.
Yeah. So you could put plus 17 there if you wanted. You could put plus 7, plus 3. Any real number could go there. You could do +0 and not write anything, and it would still be right. So that part isn't necessary when we officially work backwards. I think that's our 6th unit, where we officially work backwards. We're unofficially working backwards right now. Okay? That's officially working backwards is a fancy area of mathematics called integration. When you think of calculus, there's two main things that happen: derivatives and integration. And really it's finding slopes and working backwards. And then all the crazy math that happens as a result. So right now, we're just developing shortcuts so that we can do very complicated, crazy math using shortcuts easier. Here's another one. -3 cos x. What would it have been originally? +3 sin x or -3 sin x? -3 sin x. And then 5x. And then plus 17. So, yes.
Cos x becomes negative sin x, right?
Right.
And 3 was already negative, so that can't be.
We're working backwards now. This is where the positive and negatives, when we start working backwards, really mess you up. Because derivative of sine is positive cos. So working backwards with the negative cos, it stays negative to sine. The working backwards is like, yeah. You think your head hurts now. The working backwards. So that's why I always say, if you remember the graphs, you'll be able to work forwards well. And if you can work forwards well, whenever you work backwards, you can always double check by working forward again. But if you try to memorize them, your brain will get them mixed up and you will make a negative in the wrong spot. Almost guaranteed. Even if you learn them with a good way, you can still make that mistake easily. So here is shortcut number 3 for the day. Anytime you have a tan x, its derivative is 1/cos squared x or secant squared x. And derivatives with the shortcuts is all about being able to recognize which shortcuts you should use. I see a tan x, probably going to have to use that shortcut. I see an x squared, probably going to have to use that shortcut. What other shortcut is here? The times one, also known as the product rule. So take out my highlighter. Yes, I have multiplication and I have this one times this one. So what is that shortcut? That shortcut says keep the first one the same. Multiply by the derivative of the second one, and that's our new shortcut. Okay, so if you've been remembering your shortcuts in the evening, now you have more to go through. You're going to have 6 new ones by the end of today. We've done 3. We have 3 to go. And then keep the second one the same. Times by the derivative of the first one. Okay? So this unit sort of goes like this. If you know the shortcuts, the questions are easy. If you don't know the shortcuts, you're screwed. Basically, right? Like there's nothing, like, are you going to pull out the definition of the derivative and see if you can figure it out? No, right? Like look at, we did the sine and the cos one. You're like, oh, I forgot it. I think I'll just prove it again. If you don't remember the shortcut, your chances of remembering the proof are not good. So, that's this unit in a nutshell. Know your shortcuts very well. Okay. We got a cotangent in here. We haven't learned that shortcut yet. But 1 over cotangent is tangent. And that you know a shortcut of. So these first two are a product. So we have a product rule here that we'd have to use a shortcut for. And then we'd have to remember the shortcut for the 3 to the x and the shortcut for 10. So what do? For those two together, we are going to keep the first one the same. The derivative of 10 is secant squared x. That's a new shortcut. Then we keep the second one the same. And the derivative of 3x is 3x natural log of 3, which was a shortcut from the other day. Plus 1 over cotangent x you recognize is the same as tangent x, and you have a shortcut for that, which is just secant squared x. And if you show someone that doesn't know calculus, you can say, hey, this is the question, this is the answer. Do you understand calculus? And they would look at you like, what just happened? But we used 1, 2, 3. We used 3 shortcuts in this one, plus an identity that you knew that cotangent was 1 over x. Hope you didn't get any of that on your cape.
At the board.
Oh.
Maybe give him the Kleenex box.
This is costume.
It's kind of Halloween themed though. It's a good day to get a bloody nose. How do we find an equation of a tangent? Well, a tangent is a line. Strategic that the doctor suit guy is helping. I like this. Right? What do you need for an equation of a tangent line?
A slope.
A slope and
A point.
a point. Well, at the origin, that's our point, right?
0.
0, 0. We need to find our slope. Our derivative gives us all the slopes. If we want to find the specific one when x is 0, we plug in 0, which is 1. I got more. Hopefully we won't have to amputate. And once we have our slope and our point, it's just y equals x. I mean, 0, 0 is technically your y-intercept too, right? So you could use y equals mx plus b. I think it's hilarious that you've got rubber gloves as well. Norman's just sad that he was sitting so close. And our last 3 shortcuts. If you have a cosecant, the shortcut for cosecant is a negative cosecant times cotangent. If you have a secant, the shortcut for secant is a secant x times tan x. Which is kind of cool, because if you think of your identities back in grade 12, you know you have the tan squared theta plus 1 is secant squared theta? So you're like, tan squared and secant squared already had like a little thing going on in grade 12, right? And now the relationship is deepening in calculus. Same thing with cosecant and cotangent. And then you have derivative cotangent. There you got cosecant squared again. So it's sort of like, okay. They have something, there's definitely something going on here, right? You had your suspicions in grade 12, right? They were spending way too much time together. But now, there's definitely something going on. So now let's use our new shortcuts. Or these. Right? And technically I would say the relationship between tan and secant is a little bit more positive than the relationship between cosecant and cotangent, right? Because you can see that there, right? What's the derivative of tan? Positive secant squared. What's the derivative of cotangent? Negative cosecant squared. Okay, so here I got 3 cotangents, it's going to be negative 3 cosecant squared x. And negative cosecant with another negative will be positive cosecant cotangent. If you don't like the 3 new shortcuts, you can always change cotangent to cos over sine and use your quotient rule with old shortcuts. So it's like, I'm going to admit, I don't like these last 3 shortcuts as much. I'm like, oh, it's one of those last 3 shortcuts. I'll just change it back to sine and cosine and use those other shortcuts. Perfectly fine. However, this is still quicker if you know the direct shortcut, because then you don't have to use the quotient rule. Second derivative. Well, the first derivative wouldn't be a problem. That's one shortcut. But then if you wanted to do the second derivative, what other shortcut do you have to use? The times one. I like how we avoid the word product at all costs here. The product rule. With a negative sign out in front, I can put that in negative with the first one. So what do we do with product rule? Keep the first one the same. Shortcut for cotangent, negative cosecant squared. Plus, keep the second one the same. Shortcut for cosecant, negative cosecant would be cosecant x, cotangent x. Then, we need to find out what it's equal to when you plug in pi over 6. So I'm going to simplify things here a little bit. I multiply those together, distributed, and we have to go to our pi plate to know your unit circle for AP calculus as well. What is cosecant of pi over 6?
Two over square root of 3. Wait.
2. Because sine of pi over 6 is 1/2. So cosecant would be 2 over 1. And then that gets cubed. So this would also be 2. Tan of pi over 6 is root 3 over 3. So cotangent of pi over 6 will be 3 over root 3. Square all those, combine your like terms. Halloween's such a good day. I'm already up 3 chocolate bars above average. Many chocolate bars, not full.
What's average?
My creative thinking right now says I'm going to design a new 2-week weight loss program where you pretend the other 50 weeks of the year are gone. And then your 2-week weight loss program will work very well for you. Do you think it would work? The other 50 weeks might be a little dangerous. Probably a good reason they have only one day of video that. Find an equation. What do you need for an equation of a line? You need a slope and a point. And they gave us the point. How do we find slopes? Slopes of tangent lines are the derivative. What's your shortcut for cotangent? You don't know. You got some work to do, right, over the week? 3 new shortcuts today? Negative cosecant squared. Maybe. Yes. If you plugged in pi over 4, because that's our x value, what is sine of pi over 4? Square root of 2 over 2. So cosecant of pi over 4 would be 2 over root 2. That gets squared. That simplifies nicely to just negative 2. That's the slope of your tangent. What equation are we finding? Normal. What's the slope of our normal?
1 over 2.
Flip it. Negative reciprocal. Flip it and make it positive. 1/2. And once you have your point and your slope, you could use y minus y1 equals mx minus x1, or y equals mx plus b. And you simplify it, which doesn't look that simple, because you get a 1/2 x minus pi over 8 plus 1. I guess technically, if you wanted to really put those last numbers together, minus, I'm going to put a plus sign here, minus pi plus 8 all over 8 is your beautiful y-intercept. If you got a common denominator, you could make that into a single fraction and get one value. So you know how we did double derivatives, second level derivatives? We got one coming up here. The 51st derivative of sine. What's going to happen? Because sine goes to cos. Cos goes back to negative sine. Negative sine would go to negative cos. Negative cos would go back to positive sine. Do you see a pattern happening?
Yeah.
Right? I could do the first one, and then I could do the second one, and then I could do the third one, and when I get to the fourth one, I'm back to where I started from. When's the next time you'll be back to where you started from? 8th one. Back to where you started from again at the 12th one. What's the closest one to 51 that you'd be back to where you started from?
48.
48? Does that make sense?
Be negative cos x.
48th one would be back to where you started one. 49th, 50th. Oh, 48th. Ooh, there we go. Equal sign just needs to get back to where we started from. Got a little. If that's the 48th one, back to where you started from. This one would be the 49th one, the 50th one, 51st one. Or you could say you'd be back to where you started from at the 52nd one. So the 51st one. Whew. Whoever decided numbers should have like weird, like first, second, 51st,
Is this the end of the unit?
52nd. Are we done our unit?
Yeah.
All right.
Yeah.
That's on Monday. It might be, but not next Monday. It could be another Monday after that. Right today. First take-home quiz, though, is due on Monday. And you have shortcuts to remember.
All
We added 6 new shortcuts today. Make sure you're going through those ones in your head, right? If you remember that secant and tan have like a relationship going on, it might help you.
We might think right through Otani's